Here we're looking at solving trigonometric equations using fundamental identities, which I haven't seen this in other books, so it's kind of interesting to see this come up. So again, from the book, while algebra can be used to solve a number of trigonometric equations, we can also use the fundamental identities because they make solving equations simpler. Remember that the techniques we use for solving are not the same as those for verifying identities. The basic rules of algebra apply here, as opposed to rewriting one side of the identity to match the other side. In the next example, or examples, we will use two identities to simplify the equation. So let's see what happens here. So I use identities to solve exactly the trigonometric equation over the interval from 0 to 2 pi. And we have cosine x cosine 2x plus sine x sine 2x. And this matches up with one of our formulas, the difference formula. So this over here can be condensed into cosine of the first angle minus the second angle is the square root of 3 over 2. So cosine of negative x is the square root of 3 over 2. And since cosine is an even function, that means cosine of x is the square root of 3 over 2. And where does this occur from 0 to 2 pi? Well, cosine is positive in the first and fourth quadrants. So we're looking at x being pi over 6 and 11 pi over 6. Okay, let's go on to another one. Solve the equation exactly using a double angle formula. So we have cosine 2 theta equals cosine theta. I notice this one that didn't give us the restriction, so we'll have to do the plus 2 pi k in the end. Okay, so cosine 2 theta could be written, and because this is cosine, let's keep it in terms of one of the trig functions. So we'll go with cosine, or 2 times cosine squared theta equals, or that's minus 1, equals cosine theta. So we have 2 cosine squared theta minus cosine theta minus 1 equals 0. So if I said u equals cosine theta, I'd have 2u squared minus u minus 1 equals 0. And this could be factored to be 2u plus 1, looks like, times u minus 1. That gives us the negative there. So 2u plus 1 equals 0. Means 2u equals negative 1, or u equals negative 1/2. So we want cosine theta to be negative 1/2. So for this, theta would be, so we're looking again at, not again, but we're looking at the second and third quadrants. So it looks like it's going to be 2 pi over 3 plus or minus 2 pi k. And theta would be 4 pi over 3 plus or minus 2 pi k. 2 pi k. There we go. Now, for the other side, we have u minus 1. So u equals 1. So where's cosine theta going to be 1? Well, it's going to be where theta is 0 and 2 pi. So I guess we could just say it's going to be 0 plus or minus 2 pi k. It's not as exciting as I thought it would be. Okay. So those are our solutions. I think I missed one. No, I got them both. I got them all. There you go. 1, 2, 3. Okay, fun stuff. And let's go to the third example from this part. Solve the equation exactly using an identity. So we have 3 cosine theta plus 3 equals 2 sine squared theta. Well, we know that sine squared theta plus cosine squared theta is 1. So solve for sine squared theta equals 1 minus cosine squared theta. So we have 3 cosine theta plus 3 equals 2 times 1 minus cosine squared theta. So we have 3 cosine theta plus 3 equals 2 minus 2 cosine squared theta. If I move everything over to the other side, I'm going to subtract 2 and then add 2 cosine squared theta to both sides. We'll end up with 2 cosine squared theta plus 3 cosine theta plus 1 equals 0. So I'm going to do a u substitution. U equals cosine theta. So we have 2u squared plus 3u plus 1 equals 0. So that's going to be 2u plus 1 times u plus 1 equals 0. So we have 2u plus 1 is 0. So 2u equals -1, or u equals -1/2. What was u? It's cosine theta. We do have a restriction from 0 to 2 pi. That's good. Cosine theta equals -1/2. We just saw this one in a previous problem. So our theta is going to be 2 pi over 3 and 4 pi over 3. And then we have u plus 1 equals 0. So u equals -1. So cosine of theta is -1. So theta must be pi. So those are our solutions. Okay, that's it for this video.